Okay, I will assume not. Okay, so I just wanted to show you a visual representation of how fast it is to get data from caches. So that's the animation I was discussing about. And basically here what you can see is on the main memory itself, it is actually painfully slow to get data. And we assume about 50 and 100 times slower, right? So what I was saying is, of course, as a Go developer, if I want to optimize my application, I would like my application to leverage CPU caches, of course, right? Because that's the fastest way to get data, right? Okay, so let's talk about theory a bit here with what we call locality of reference. So basically, locality of reference, that's the following. There are different applications, but we are going to focus on only two of them. And we can say if a particular memory location is referenced, it is very likely that the same location will be referenced again in the near future. And that's what we call temporal locality. So here is a very small example where we are going to say I initialize a counter and I initialize a slice, and I'm going to iterate over this slice, and every single time I will increment my counter. So where do we see in this particular example temporal locality? We can see it at the sum level because we keep updating the same variable over and over. We do see it as well on the index as well because we keep both referencing it and updating it here at this stage, right? And we see it also at the length for the bound check whenever we want to check whether we are going to exit the loop. So that's the goal, that's the principle of temporal locality. And that's one of the reasons to have CPU caches, because we are going to say, I want, if I accept the same location, I want this, the second and the third accesses basically to be as fast as possible. So that's temporal locality. And there is another principle which is going to be very important for us. If a particular memory location is referenced, it is likely that nearby memory location will be referenced in the near future. Nearby memory locations. So that's what we call spatial locality. And here in this example, where do we see it? We do see it on the slice itself. And we are going to do a focus in the next slide in this principle of spatial locality. So here we have a slice. That's the representation we have in our heads, right? And we have, in this example, 8 elements, whatever. And that's a possible representation that we have into the main memory. And we have to know that the main memory is organized in what we call blocks. And the blocks, a block, that's something that has a fixed size. So here that's a possible allocation. Of course, the slice could have been allocated at the very beginning of the block, at the middle or whatever. It's for the sake of the example, right, guys? So, and here, of course, we have our CPU cache. And for the time being, let's not focus on whether it's L1, L2, or L3, okay? So what's going to happen if we want to iterate over this slice? Basically, when we are going to start this iteration, we want to access to the very first element of the slice, and the CPU core is basically going to first try to get the data from the CPU cache, because of course that's the fastest way to do it. So first, we try from the CPU cache. And in this example, unfortunately, we don't have the data yet into the cache. So that's what we call a cache miss. So here in this case, what's going to do the CPU cache, the CPU is going to, instead of copying a single variable, we will copy what we call a cache line. And that's a very important principle. We are going to copy a cache line in this example. And what's a cache line? It's just a contiguous segment of memory of a fixed size. And usually we are talking about 64 bytes. So again, pretty much slow. 64 bytes, it's just 8 in 64. So we are going to fetch the data into the CPU cache, right? So what's going to happen when we keep iterating? We are at the second element, and basically now this time it's a cache hit because we already have the data into the CPU cache. And when we keep iterating over it, everything is still part of the CPU cache. It's just cache hit. So what's going to happen when we are here at this stage now? So basically, it's going to be what we call, again, a cache miss. We are going to refetch again the data. And now everything, while we are going to iterate on it, will be again part of the CPU cache, right? So in this example, we can say that we had a number of cache miss, of course, but they are limited. And that's what we call compulsory miss. That's basically a mandatory cache miss, because obviously the data lives into memory. So at some point, we have somehow to get the data from memory. But the way we do it, we fetch cache line so that we will be able to reduce the number of cache miss. Also something to say here, that's a pure theoretical model, because of course other applications can run at the same time on the same core and utilize your kind of own, your CPU cache, of course. So that's of course the theory here. And something as well to say, there is something, I mentioned that we have both L1, L2, and L3. There is what we call the cache placement policy, meaning that where do we want to basically fetch a line, be it on L1, L2, or L3. And there are different policies. One of them is to say that L1 and L2 are what we call inclusive, because L1 is just a subset of L2, and L3 is sometimes called what we call a victim cache, because when a cache line is evicted from L2, it goes into L3. But does it matter that much? Not that much. I'm something for the CPU designer. But for us as Go developers, what we want to do is helping the CPU. And to help the CPU, our application needs to leverage locality of reference, what we have seen, keeping things contiguously allocated, right? And there is another very important principle here. It's about predictability. So locality of reference and predictability. We're going to see two examples. On the first one, we can say, okay, if I iterate on the linked list, and I will, for example, try to allocate it contiguously, meaning that it's the scope of a single function, for example, and I am not going to keep updating it. Normally, everything should be allocated contiguously. So in terms of performance, it should be pretty much decent, right? So that's this example where we have here a value, which is an int64, and we have a pointer, which has a size of a word, and a word, that's something which is mapped onto the CPU architecture. So if it's a 64-bit architecture, a pointer will be 64 bits. So exactly the same size of this int64. So in memory, it should be something like this, right? So in blue, we have the value, the element we are interested in. For example, we are going to increment the counter again based on the value. And the gray part is the pointer that we have in main memory, right? And on the right-hand side, we are going to do something which is kind of similar here. Basically, what we are going to do is to say, I will iterate only over one element out of two. So in the main memory, what we have in blue, that's what we are interested in, and in gray, what we are not interested in. So what happens if we run a benchmark between iterating on a linked list and iterating on a slice with only one element out of two? Actually, the linked list iteration is more than 200% slower, so painfully slow. And here, what do we have? We have a possible spatial locality. And actually, we are not sure about that because, well, it depends on various reasons where sometimes we believe that everything is allocated contiguously, but sometimes not. Everything will be part, the next pointer might be part of another block, basically. So we have a possible spatial locality here. And for the CPU, it is not predictable. It's not predictable to know whether or not things are contiguous like this with a linked list. So basically, the CPU is not going to fetch the CPU cache line, hence leading to this, slow benchmark. Okay, so there is another example I wanted to discuss about, guys. It's what if we need to iterate backwards on a slice? So here, that's the main memory. And we're going to say, I'm going to iterate backwards, right? So let's try to run 2 benchmarks. So I wanted to show you just a loop here. And what if we run both? We can see that both are actually have the same, more or less the same execution time. So we do have spatial locality, of course, because with a slice, everything is allocated contiguously. And more importantly, in this case, the CPU was able to predict that we were iterating backwards. So in a sense, a CPU is kind of smart, right? Even in this case, he's able to say, okay, I know in this case that I'm going to prefetch this line because I know I was able to predict that you are going to iterate backward in your application. And just something to mention here, it's slightly faster, as you can see here, because actually the bound check with the backward iteration is slightly faster. Here, we just need to check one single bit. So for us, one of the challenge as well as developers is to say, how can I make things predictable for the CPU? There is this important concept of striding. And basically, a striding, it's how does a CPU work through my data. There are 3 types of stride. The first one is unit stride. Basically, I'm going to iterate over each element, something like this. And we have a perfect spatial locality and everything is completely predictable for the CPU. We have a constant stride. For example, 1 element out of 2. It's something like this. And basically every single time, the CPU is going to jump from one address to another like this by jumping the memory location we are not interested in. So here we have less, it's slightly less efficient because we have less of spatial locality, right? But it's completely predictable for the CPU. So for example, the CPU is able to say, okay, I know that if you are going to jump from 64 bytes away, so a cache line, it will not fetch the cache line because it will say, okay, I will just have only 1 element into this cache line, so it does not make sense to fetch it. So that's the type of reasoning that the CPU is able to do. And the last one is the one we have seen with the linked list. The data might be spread across memory. It might be, it might not, but for the CPU, it doesn't know. It's completely not predictable. And in this case, we can reach terrible performances, right? Okay, so let's take a step back, guys. What have we seen so far? We have seen that CPU caches are extremely fast, right? We have seen as well that a CPU doesn't cache a single variable, but a cache line. And also we have seen that we can help the CPU if our application leverages locality of reference, so things contiguously allocated, and predictability with a constant or a unit stride. Okay, so let's move on and let's talk about data-oriented design. Basically, that's a concept which came from Mike Acton, who said that what we are doing all days as developers is just transforming data, be it when we are additioning data, when we are concatenating strings, for example. What we do all day is just transforming data from one form to another, right? And the way we tend to structure our data is based on object-oriented design. And in a sense, well, okay, of course, in Go, we do not have object-oriented design as such because we do not have inheritance, but still, when we create structure, we are going to mirror basically how we interact with the real world, right? It's our way to do it. It's the most easiest way for our brain to do it. But still, according to Mike Acton, hardware does not like objects, and we are going to understand why in a moment. So basically, he proposed to shift our way to structure data from an object-oriented design to what he called data-oriented design. And data-oriented design is just about organizing data in a way to get the most value out of each cache line. That's fairly simple on the paper. So we are going to see 2 concrete examples. What does it mean really concretely? How can we apply data-oriented design? So here we are going to see structure alignment, we're going to talk about it, and a good fight between slice of structure versus structure of slices. So with structure alignment, we are going to see run two benchmarks. On the left-hand side, we have a structure containing a Boolean, an int64, and another Boolean. We create a slice on top of it, we iterate over it, and every single time we increment a counter based on element I, which is the int64. And on the right-hand side, we have this structure, which is slightly different because we just have the int64, which is allocated first before the two Booleans, and the rest of the benchmark is exactly the same. And we have to know something. In Go, the size of a structure is every single time a multiple of the word size, meaning that on a 64-bit architecture, it's 64 bits. So every structure is a multiple of 64 bits. So let's come back to our first data structure. We have said we have a Boolean, an int64, and a Boolean. Here is how it is allocated in memory. Basically, first we allocate the Boolean, then we allocate the int64. There is no space left on the first block, so we allocate it on the second block. And the next Boolean is going to be allocated again in the next block. Why? Because in Go, we do not have structure compression. We might have been assuming that this Boolean would be allocated here, but it's not the case. It's up to us, actually, to make it compact or not. And that's what we call structure alignment, because everything is aligned, is a multiple of the word size. So in this very case, we have 24 bytes. And on the right-hand side, we have this slight modification. Does it change something? Kind of, because as you can see here, first we allocate the int64, and now we have the two Booleans, but they can both fit into the same block, right? So in memory, it's gonna take us only 16 bytes. And if we create a slice of 10,000 of element, it will require 3,750 cache lines. And on the right-hand side, and as you can see, I did it at scale. So you can see that this stage here, this allocation is way more fragmented, let's say, in memory. Here, with the same number of elements, it requires only 10,000, it requires only 2,500 cache lines in this example. So if we run a benchmark between both, if our structure is compact here, it's about 30% faster. So it's very interesting because most of the time when we talk about structure alignment, we have in mind the memory footprint. We want our application to allocate less memory, for example, because we want to pressure less the GC and everything. But it's not the only impact. One of the impact as well is to say that iterating over a compact data structure is more efficient because it will require less cache lines. And we have been able to arrive to this conclusion because we know how the CPU is actually working. So of course, it does make sense if we want to iterate over it. It will require to fetch less cache lines, right? Okay, so here is the next example, slice of structure versus structure of slices. Here, what we do is we create a slice of a structure containing element A and B. And on the right-hand side, we are going to create a structure containing slices. So here, that's the structure. Here we have two slices of A and B. And in both cases, what we want to do is to say, I will increment a counter based on only element A. So here, what we do in this example is to access the index first, then the element. And on the right-hand side, we access first the element, then the index. So it's more or less the same. It's just a way to structure the data, but it does not change things drastically, I would say, right? So what's the impact of this in memory? In memory, and things are again at scale, and in blue, that's the part that's still the same color code. In blue, that's the part we are interested in, and in gray, the part we are not interested in. Here, we just increment the counter based on A. So in this very case, it will require 11 cache lines, whereas on the right-hand side, because we are going to iterate over a slice, everything will be allocated contiguously. So if we want to iterate only on A, it will require only 4 cache lines in this case, only 4 compared to 11 cache lines. And on the left-hand side, if we think about it, it's a constant stride, meaning that we are going to jump from here to here. And that's exactly what we have said. We have predictability, but we have not a great spatial locality, right? Whereas on the right-hand side, we have a unit stride, so both predictability and perfect spatial locality. And if we run a benchmark, the right-hand side is 30% faster. 30% faster just by the way we kind of organize data. And again, I wanted to have to implement stuff on a concrete example. So I wanted to take something that is really CPU bound and really computational heavy. So I took something from the Go sources directly. There is a package called Flate, and Flate does basically a compression algorithm, doing some stuff. I don't even know what's doing. So I basically copied this line from Wikipedia. But it's computational heavy, right? So here, that's the current implementation we have in Go, right? And there is this little guy here called hcode. And basically what we see here, it's a slice of structure, right? Containing both two elements, code and len. And on the right-hand side, it's my modification. And here what we see instead, we have a structure of slices, right? So it's a very simple change. And I found actually in the implementation that we had a 5 iteration loop on either hcode.code or hcode.len. And this example, so my modification was just because before we were accessing the index, then the element. And I just modified things to say here, I'm going to access the element first at a particular index. And my change is very simple, right? And I wanted to, before to run a benchmark, to give it a try, to see if I was able to get some metrics to see if I was able to validate that my understanding was correct or not. And I took something which is called Xcode instruments. It's working on Mac. There are plenty of other tools, but this one is pretty cool. We have a nice UI and everything. So here what we see is in this column, that's the number of L1D, L1 data, right? Cache misses. And the first line, it's the current implementation we have in the Go sources, the Flate one. And this one is Flate 2. It's my minor modification, I would say. And here you can see we are switching from 22 something to 13 something. So it's almost a reduction of 50% of L1 cache misses just because of this small change. And if we run a benchmark between both, so in blue, it's going to be the current implementation. In green, it's going to be the structure of slices, so the change. I was able to get faster results depending on the benchmark between 20 and 28% faster. So that's pretty amazing, right? And again, we have been able to reach this because we understand how the CPU is working, because we understand how cache lines are actually working, and that's it. That's pretty cool, right? So what have we seen, guys? We have seen that we can both design algorithms to leverage CPU caches and organize data to get the most value out of cache lines. And we have seen as well that a unit stride, that's the best way for this, because we have perfect spatial locality and we have predictability as well. Okay, so let's dive into another example. So this one is not straightforward, but it's really fun. Well, at least in my opinion. So let's stay focused. Okay, we are going to have fun here. So let's assume here we are going to say I create a 2-dimensional array containing int 64s. And we assume that we have a cache line which is 64 bytes. So we can store up to 8 elements per cache line. In this example, we're going to say I have a column, number of columns, which is variable, which is n. And I have a certain number of rows. And what we are going to do in our algorithm is to say, I want to traverse each row multiple times, but the first 8 columns only. So we are going to do only on the first 8 columns. So it's going to be something like this. We start at the first index, We iterate over each row, only the first 8 columns. And once we arrive here, we have said that we are going to traverse it multiple times. So we come back again, and we are going to traverse it like this again and again and again. So basically, the algorithm would be something like this. We have 3 loops, so multiple times on each rows, and the first 8 columns only, right? And something important here, we want to make sure that the number of rows is small enough so that basically our internal data structure, only the first 8 columns, can fit into the cache line. So it means that whenever we are going to come back to the first index, everything should be already part of our CPU cache, because normally everything can fit into the CPU cache. And there is something important. What if I tell you guys that in regard of the execution time depends on n, which is the number of columns. What is even n? In this example, it's a factor that does not even appear in our algorithm. And depending on n, the execution can be up to 2 times slower. 2 times slower for a factor that we can't even see here. That's crazy, right? So let's try to understand the logic. There are different ways to have caches, and we are going to see first the first possible way. So here what we have said, something to mention first, a block in memory, it's something that is referenced by an address. Of course, here we are storing per block multiple bits, right? Multiple variables and everything, but it's always a block is referenced by an address. So that's basically the first address of the first memory here. And here what we are going to do, as we have said, we are going to just iterate on basically each blue block, and every single time we are going to jump like this, meaning that we are jumping from one row to another, right? So at first in our program, we are going to say, of course, I want to load the first address. That's going to be one of the first instructions, right? And in what we call a fully associative cache, we may have to traverse the whole cache to check if an address is present. The whole cache. So here in this example, I have only 8 lines, so it's not a big deal. But on my CPU core, I have on my L1D 512 lines. So in the worst case scenario, I will traverse 512 lines, and it's going to be a huge waste of CPU cycles just to see that, right? So there is a solution for that brought by the CPU designer. It's called partitioning, and it's a concept we should already know, right? When we are doing maps, for example, underneath, it's using a form of partitioning, right? So we are going to see an example with partitioning data. So at first, we load the address. We load the address 000. And what we can say in this example, and that's only for the sake of this example, we store 4 bits per block here. Of course, in the real life, we have more than 4 bits per block. But here, just for this example, right? And we can say that 4 is equals to 2 power 2. So this little guy here is what we call the block offset, meaning that the 2 least significant bits are what we call the block offset. We will understand the logic. So let's move on. And with this way of organizing the cache, a cache is partitioned into what we call sets. And a block, a memory location represented, which represents a block, can belong to only one set. And that's what we call, instead of being fully associative cache, it's a k-way associative cache, meaning that we have k lines per set. So in this example, we have 8 lines. We assume a 2-way associative cache. So we can easily compute the number of sets by doing a simple division. And here in this example, we have 4 sets. Why 4? Again, because we have 2 lines per set, because it's a 2-way associative cache, right? And 4, it is equals to 2 power 2. So this little guy here represents what we call the set index. So this address, we already know, because of the set index here, 00, that it belongs to set 0. And that's the purpose of this partition cache. We already know that this address is going to be fetched only here or here, right? And the last part is what we call the tag bits. And the tag bits, that's something we associate to the cache, and we will understand the logic. Basically, when we are here, we fetch the data, and we are going to associate the tag bits, which are in our case, what remains actually in the address, so the 3 most significant bits here. So what have we done in our matrix? Let's come back to our matrix. What we have done is we are here, right? And we say, I'm gonna load the first address. So we are going to fetch a cache line. And now once we iterate over it, everything is already part of a cache line. So we should have just cache hit. And now we are going to jump basically to the next row, right? So what we're going to do now is loading this address 001,000. And here what we see is we have the same set index. So it will belong to this set index, to the set 0. And what we are going to do with a k-way associative cache, we are going to traverse only the set the address belongs to. So we are going to traverse only the set 0 in this case. And we are going to compare only the tag bits. No need to compare everything, just the tag bits. Here we see that the tag bits does not exist in our tag bit structure. So basically, we are going to fetch the data and associate again the tag bits, right? So let's move on again to the next row, and things are going to get a bit interesting here, because we can see again, we are lucky or unlucky, we don't know yet, but it's still the same set index. So how is the CPU going to react? Is it going to be kind of nice with us and saying, okay, I know that the rest is not allocating, so don't worry, I will anyway allocate it here? Of course not. It will not. It will just say, because it's a k-way associative cache and the block belongs to only one set, it will fetch the cache line into one of the 2 possible lines, right? And that's what we call cache replacement policy. Internally, there are policies to say which line am I going to replace. And one possible implementation is what we call the pseudo list recently used. And whenever we are going to again jump to the next, it's going to be again the same logic. Unfortunately, it's the same set index, and we are going to replace another address. So what is the impact of this? We have said that we are going to iterate over and over on this structure. So once we are at the end, we are going back to the first address, right? And in this case, what we are going to have, it's a cache miss, because we do not have the data anymore. And why don't we? It's because the distribution of our cache is not even at all. We used only one set in this example out of 4 sets in total. So it will generate, in this very case, it will generate a lot of cache misses, and that's what we call a conflict miss. We have seen the compulsory miss, which is a mandatory miss, basically. There is another type of miss, which is the capacity miss, because our data structure does not fit into the cache. And here we see the conflict miss, because basically our partitioning is terrible. And this constant stride, this jump that we see here, that's what we call a critical stride. We reach a critical stride whenever we use only one set out of all the possible sets. So let's come back to our example, guys. In our example, we had this, and there is a way actually to compute the critical stride. It's very simple. It's the number of sets multiplied by the cache line size. And in my example, in my CPU core, the cache line is 64 bytes. I have on my L1D 64 sets. So the critical stride is 4 kilobytes. And we can compute with how many number of columns do I reach this critical stride of 4 kilobytes, because everything is just in 64. We can do a simple computation to get this number. And we can say that we reach this critical stride if n is equals to 512. So it means that if n is equals to 512, we are going to use only one set of the cache. And let's try to run a benchmark. And we can see here, as you can see, we can have a variance of 100%. Here, with 512, so with a critical stride, it's 2 times slower than if we had only one column, if we have 513 columns. So in this case, if we were adding a single column, our algorithm would be 2 times faster, which is a bit crazy, right? But now we understand it. It's simply because caches are actually partitioned. And something as well to mention, whenever you divide a critical stride, if you divide it by 2 or by 4, by 8, and so on, you are going to use only 2 sets, only 4 sets, and so on and so forth. So if you divide it, basically, you are going to go to tend to something that is closer to the best possible solution here when we have a perfect distribution. All right, so what have we seen? CPU caches are partitioned, and it's a way to get to see if an address location is already part of the cache. Way more fast, actually, way more faster, right? And depending on my data, actually, we can see that our application can occupy a fraction of the cache only. If we are not allocating things well good enough, let's say, we can only occupy a fraction. And we have seen this critical stride, meaning this stride where we are going to jump on something. And unfortunately, the result of this jump is that we are going to use only one set. Okay, so the last part, which is with concurrency. So why concurrency at first? Here is an example of a well-known benchmark on a sequential code, which is called single-threaded integer performance, whatever. And we can see here is that since about 2005 or something, things are not scaling linearly. We tend to reach a kind of threshold, that it's a kind of logarithmic curve, right? Like this. And since about 2005, the focus of CPU vendor has been to say, I'm going to focus now on multi-cores and hyper-threading architecture. And hyper-threading, that's what we said at the very beginning, having multiple logical core, virtual core, per physical cores, right? And there is this great post in 2005 saying the free lunch is over. And basically what Herb Sutter said, we cannot rely solely on the hardware to make our program faster. And it was in 2005, guys. He said that concurrency is the next major revolution in how we write software. And which is pretty cool because in Go, we have great concurrency primitives. So we can consider ourselves pretty much lucky, right? So here is an example. And this is, I swear, this is my last example of the day. So here, this example is kind of simple, actually. We have a structure here containing a single integer. And we are going to initialize to allocate 2 instances, struct A and struct B. And we are going to spin up 2 goroutines. In the first goroutine, we use only struct A.n. And in second goroutine, we use only struct B.n. And in the end, we wait and aggregate the results. And here, that's a completely valid code, meaning that it's a Racefree implementation. Here, both are using their own data. The first goroutine is only using struct A, and the second goroutine is only using struct B. But there is a huge problem with this small test. There is a huge problem. And we are going to understand it why by coming back to theory here. So at first we have said we have blocks, and here we have 2 cores, right, having their own L1D. And here is an example of a cache line. Let's assume we have a one goroutine that want to access to var1, and another goroutine that want to access to var2, another variable, which are whatever we want, right? Here, the CPU, what the CPU is going to do is basically fetching the data. And on the right-hand side, we are going to fetch again the data. So as we can see, both variable belongs to 2 different cache lines. And now what if both goroutines want to update their own lines? Basically, the CPU does not know whether our goroutine will just update var1. For him, the granularity is just at the cache level. And the goal of the CPU here is to guarantee what we call cache coherency. So basically, we'll be able to say whenever you modify a cache, I'm going to be able to preserve the coherency. And there is an internal protocol called MESI protocol. Well, no need to spend too much time here. But why does it matter? Why does it matter that the CPU is going to preserve cache coherency? Let's assume in our first case, we update the first variable. And in the second case, what's going to happen in the sake of coherency, the CPU cache is going to mark this line as invalid. So basically what we are going to do, well, most of the time, there are some slight details, but anyway, let's consider that we are going to fetch the data from main memory. And what if in the worst case scenario, the second one is also going to update the variable? The first line is going to be marked as invalid. So we are going to have to fetch again the data from the main memory, and again and again and again. And this principle is called false sharing. Basically, when a cache line is shared across two cores with at least one coroutine being a writer, we will have what we call false sharing, because we will keep having to refetch and refetch and refetch again the data from the main memory. And we can see here that basically sharing memory is just an illusion, because the way CPU cores are implemented is just an illusion to believe that this coroutine and this coroutine share the same variables. So here our issue, if we come back to our implementation, was that basically the two structures were allocated contiguously. So basically struct A.n and struct B.n, they belong to the same cache line. So when we were updating it, we were going to trigger false sharing, which was, as we said, keep refetching data because of this, because both belong to normally the same cache line, right? So how do we prevent false sharing? There is a first solution that we should already be aware of, which is about to say, do not communicate by sharing memory, instead share memory by communicating, right? So here in this case, we just keep a local state, we communicate using a channel, and we aggregate, and everything is fine, right? Great. And the second solution, which is also interesting, is about padding. And padding, that's just a way to say, I'm going to modify slightly my data structure to say before and after, I'm going to allocate something that has the size of a cache line. And in Go, we have a constant, which is called CPU.cacheLinePad, and which is 64 bytes on a 64-bit architecture. No, sorry, I'm mixing stuff, sorry. Which is the size of a cache line, excuse me. So here, if we come back to our example, basically, we can make sure if we allocate stuff before and after that both variable 1 and variable 2 are going to belong to their own cache line. So we will not have any false sharing at all. And if we run a benchmark, we can see that false sharing is pretty huge. And in both cases, for channels and padding, it's about 60% faster. So padding is hard. There is a great example, a great blog post that you can read from Dave Cheney. But sometimes it's necessary, be it in the context of the library or something, when we are obliged nonetheless to share memory because we have a closure. Well, there are some cases where sometimes we are obliged to share memory, and we have to make sure that basically we do not share cache lines across different Go routines like this, right? Okay, so here is the conclusion. So we have seen a lot of examples, guys, where we were able to kind of optimize our application because we knew how basically the CPU is actually working underneath. So it's pretty cool. But if we had to take three main takeaways from this presentation, first, and that's something that is very important here, sharing memory is an illusion. And that's the way things are working underneath, actually, because some CPU caches are what we called on-die. They belong to the same, to one CPU core. So basically, you can have cases where your data is actually copied onto two different cache lines. So if we believe that from a development perspective, we share memory across Go routines, it's a complete illusion because the data is going to be copied. And we have seen also examples where a code that looks perfectly valid from a Go perspective might still be a problem at CPU level. We have seen the example with the caching distribution, because we had this critical stride leading to a terrible distribution in our data, leading to what we call conflict miss. We have seen also the example of false sharing, of course, leading to have it to refetch the data again and again. So definitely a code that looks valid, that looks perfectly valid, might still be a problem at CPU level. And it's because we understand the CPU is working that we can avoid such problems. And last but not least, we have said that we can help the CPU with both locality of reference and predictability. And we can implement algorithm or data structures because we know these two important principles, right? What else? Something, of course, I wanted to mention here is, of course, watch out for premature optimization. Of course, we do not want to optimize our application at this level of detail, I would say, if we are going to wait for, I don't know, 100 milliseconds for an external service or an external database or something like this. So, of course, be careful about over-optimizing stuff and premature optimizing, of course. Also, something I wanted to mention here, because the more you dive into the CPU and the more you understand how incredibly smart a CPU is to execute a sequential code in a parallel way. And that's what we call superscalar processor. Superscalar processor are just a way to say, I can have multiple what we call execution units for core. So basically, we will be able to fetch data, to fetch instructions, and to execute them in a parallel way. And after that, there are ways into the CPU which are implemented to say, I can even trigger out of order execution and reorder the things in the end. So a CPU is a great piece of engineering. And sometimes it's better to have a sequential code that leverages perfectly locality of reference and predictability rather than having a code which is concurrent, but which has a poor locality of reference and poor predictability. And that's something very important here. And last part, we have talked about mechanical sympathy here, and we have said a lot of stuff related to CPUs, but of course, mechanical sympathy goes beyond the very scope of CPU. For example, the B-tree data structure, the B-tree, which is one of the data structure which is used by many databases, for example, is just a way to mirror how the disk is actually working. So in a sense, that's also a form of mechanical sympathy. We know how something is working, so we can create a data structure because of it. So mechanical sympathy is, it can be applied to many different hardware level, let's say. Okay, that's it. That's the end. Thank you very much for your attention, and thank you for the GopherCon Turkey organizer for having invited me. Thank you very much.